start. So today I'm very happy to introduce Stefan Kebekus from the University of Freiburg, and he'll be talking about an Albanese construction for Campana's seafarers.
Right. Thank you so much for the introduction. I understand that I should be giving a bit of a introductory talk first, and then a regular talk afterwards, correct?
Yes,
Okay,
correct.
this is correct. So let me start with the introduction. I don't know how long this will take, 30 minutes, I understand, but let's see whether I use less time or not. So maybe I should give an introduction to C pairs and their differentials. Which is a little funny because there's somebody in the audience who knows this stuff as well as I do, and maybe much better. Pedro, you will correct me whenever I say anything stupid. So I like to start with a bit of motivation, and I like to give two different strands of motivation. So motivation number one is structure theory of projective varieties. And I'd like to look at projective varieties over the complex numbers. The structure theory of projective varieties over the complex numbers has seen a tremendous success over the last, I don't know, 40 years. Starting with a theory of surfaces pioneered by the Italian school at the end of the 19th century, beginning of the 20th century, and then again in higher dimensions, starting with the work of Shigefumi Mori. So what a structure theory of projective varieties or the minimal model program do. The minimal model program is basically a machine or a quasi algorithm. So the minimal model program is a quasi algorithm. So that takes projective varieties as an input and produces a distinguished element of or representative the birational equivalence class where positivity properties of the canonical bundles of canonical bundle or the canonical class are pure. And what do I mean by pure? Pure means something like start with a variety of Kodaira dimension 0. And obtain a variety whose canonical class is numerically trivial. Right, so we start with a variety whose canonical class is mostly zero, intersects most curves with a zero, might intersect some curves positively, might intersect some other curves negatively. So the curvature of the canonical class is a big mess. And what the minimal model program does for us, it purifies the curvature to make it totally zero. So similarly, so for other Kodaira dimensions. The canonical or the minimal model program produces birationally equivalent varieties of the input where, well, the canonical class is purely positive or purely negative, or there is a fiber space structure where the canonical class of the fibers is of pure curvature. So this is admittedly a little vague, but I understand that the minimum model program is very well known in Taipei. So let me leave it at there and basically say that the minimum model program is a big unmixing machine that takes as input varieties whose canonical class might be positive on some curve, negative on some other curve, and then outputs a variety where the canonical class is of unmixed curvature. So this is very cool, and this is very successful, but there is a major drawback in all this, is that the minimal model program really only looks at the curvature of the canonical bundle. Minimal model program looks at the canonical bundle. So this is the determinant of the bundle of one forms only. And this is basically looking at like mean curvature instead of the full curvature tensor when you unmix. So the minimal model program looks at the canonical bundle or the curvature or positivity property of the canonical bundle only, but there's much more information. There is, much more information in omega 1 compared to the determinant of omega 1. This is, I'm teaching the linear algebra beginners class this term. And of course, there's so much more information in a matrix than there is in its determinant, which is simply a number. When you have a matrix, you have eigenspace decompositions, you have You look at the Jordan normal form, which gives you a filtration of your vector space. There's so many things that you can do. Same here. So maybe as a slogan, from the point of view of minimal model theory, of the minimal model program, you can't tell a torus from a hyperkähler manifold. Because both have trivial canonical class. But I would like to look at the difference, and the difference becomes very obvious when I compare the omega ones of a torus and of a hyperkähler manifold, because on a torus the omega one is trivial, and on a hyperkähler manifold it's not. So I have a one form on a torus. I definitely do not have a one form on a hyperkähler manifold. And this already marks a difference. So what we want to, let's say, improve the structure theory coming from the minimal model program by looking at omega x, which is a finer invariant. Compared to its determinant. And you might ask, why don't I just do it? So what's this fuss with all the Campana C pairs and all about? Why, if I want to look at omega one, why don't I just look at omega one and instead start this fuss with Campana pairs? So there's one important lesson that that we learned from the minimal model program. Already the first and maybe most basic result of minimal model theory, where it all starts, the Kawamata-Vivek vanishing result, tells us that we should look at pairs. Rather than mere spaces. We should look at pairs rather than at mere spaces, and this is maybe most obvious in the Kawamata-Vivek vanishing. Kawamata-Vivek vanishing theorem. There, we look at a branched cover, and let me draw a silly little picture. This is the simplest branch cover I can think of. Z goes to Z to the M. Branch cover, it goes from X hat to X locally at the generic point of the of the branch locus or ramification locus, it basically will look like so. You might add some more coordinates and right. Oops. I'd like a look at a branched cover that locally looks like so. And then the canonical bundle. Then the canonical bundle of X hat looks like Kx hat is gamma upper star of Kx plus, what is it? M minus 1 times the ramification locus. And that looks like gamma upper star of Kx plus m minus 1 over m times the branch locus. And now we're in business. So we would like to understand the canonical bundle upstairs, and trying to understand the canonical bundle upstairs is something that involves looking at the canonical bundle downstairs, but with a, Lazarsfeld would say, Q-twist. The canonical bundle downstairs, or the canonical divisor, is twisted with a class that has coefficients that are no longer integers. They're rational numbers or standard coefficients, that is, rational numbers of the form m minus 1 over m. Right. And Campana pairs is trying to do the same thing. Is trying to do the same thing with omega 1. Do the same thing with omega 1 x omega 1 x hat instead of kx. So this is what the definition is all about. That was motivation 1, and that already took 19 minutes. So let me be a little quicker with motivation 2. Motivation number 2. So when given a manifold, let's say projective x, then right, the geometry is very much encoded in omega 1x. So we know that there's such a theory that relates the topology of X to properties of the holomorphic cotangent bundle. So then it's classically known that given an SNC divisor on X, then the geometry of X minus the divisor, though this is now a non-compact manifold, this is encoded in omega 1 x log d. Now that has been studied in and out by the early work of Deligne. So you have a full-blown Hodge theory for the sheaf omega 1 x log d. And the Hodge theory of omega 1 x log d encodes the topological properties of the non-compact variety x minus d. And what Campana wants to do is look at pairs of the form x and then a sum of a divisor with a standard coefficients. So if all mi equals 1, then divisor vanishes. I get the geometry of x. If all mi equal infinity, then we have infinity minus 1 over infinity by definition is 1. Then the divisor is reduced. Get the geometry of x minus divisor. And if the mi are intermediate, then get something new. That interpolates between x and x minus d. So that is another motivation. The Campana C pairs, if all the coefficients are 1, this gives us back the classic geometry of x and the classic sheaf of Kähler differentials. If all the coefficients are infinity, then we get the almost classic logarithmic differentials and the geometry of x minus d. And if the coefficients are intermediate, then we get something new, which in a sense interpolates between the compact and the non-compact case. This might be interesting. So the goal or the basic construction is cook up a sheaf that is between the sheaf of logarithmic differentials and the classic sheaf, where these are differentials that have a logarithmic pole of fractional order mi minus 1 over mi along the coefficients di. Right. And you might rightfully ask, what is this? So let me draw a silly little picture. Let's say we have A2 here. We have the y axis, and so on A2 And then we have 3 minus 1 over 3. Let me take 2. 2 minus 1 over 2 times y-axis. We this comes down to, well, differentials of the form. Well, dx, dy, and here I want to have a logarithmic pole of order 1/2. So this is the sheaf of log differentials with fractional pole order. So this is what we want to do. But again, you might ask, what is this? Because as we all very well understand, the root function doesn't exist in complex analysis. So the main problem here is x to 1/2 is not a well-defined function. The way to make it well-defined has been pointed out to us by Riemann. The function is not well-defined. It's a multi-valued function, but it does become single-valued if we pass to a suitable cover. But it becomes well-defined once we pass to a suitable cover. This is actually how Riemann came up with the notion of the Riemann surface. The Riemann surface for him was a construction that makes a multi-valued function such as the root function well-defined. Right. So upshot for the last minute of this introductory section is we want to define a sheaf of differentials that have poles of fractional order. Such a sheaf cannot be defined really on the space that we're living on, but it can be defined on suitable covers, which adds a host of complications to the theory, but many of these can be overcome. And once we're in a suitable cover, we have an honest sheaf. We can talk about the curvature tensor of the sheaf, which gives us much more information than merely looking at the determinant. And then we can try to emulate many things that we have seen in classic theories, such as Hodge theoretic results, curvature theoretic results, foliations, you name it, and hopefully come up with better and new structural results. Thank you for your time.
Could I ask a question?
Sure, that's why I'm here.
So yes, so could we consider also the Riemann for stack? So for instance, for the example A2 together with this y-axis. So yeah, can you consider it as a quotient stack of A2 by a Z mod 2? And
so yeah, I perfectly understand the question. I would like to point out in the next talk that while there are some similarities, the the category that you get from Campana C pairs is different from the category of a root stack. So for instance, if you have, say, your y-axis with multiplicity 1/2. Right. And you have a curve and a morphism into A2. You ask yourself, when should this morphism be considered a morphism of Campana C pairs? I haven't talked about morphisms yet, and I haven't talked about a category. I'll do this in a second, in the second half of the talk. Right. And the answer is, if the curve or the image of the curve touches the x-axis with multiplicity 2, then this is a morphism of Campana C pairs. And the 2 is the 2 that you can see here in 1/2. If it touches the x's with multiplicity 3, then it's still a morphism of Campana C pairs. The notion of a morphism that I would like to propagate in the next talk says that the condition to be a morphism is that the intersection number is higher than 2. Now, if you're talking stacks and you use stacks, root stacks, to encode tangency conditions, the way that Charles Cadman did in his fundamental paper where he introduced root stacks, then the condition is that the intersection number is a multiple of 2, and 3 is not allowed. So the categories differ, and the Campana category has more morphisms than the root stack category.
I see. So in terms of morphism, it's maybe more flexible to work with.
Yes, it's more flexible, and it allows you to talk. I mean, when you have in complex analysis, you have the embarrassing problem, or I don't know, fact, that when you take a punctured disk, the fundamental group is Z, right?
Yes.
So to give a branched cover over the punctured disk is to give a number. And this creates this big confusion because of root stacks and of Campana things. So over the complex numbers, you're always, when you say root stack, you have to say what the inertia groups are, and you can say what the inertia group is by giving a number. So Campana theory talks about multiplicities and numbers, but these two things, they completely fall apart when you go to positive characteristic, where the fundamental groups are huge, and you can't specify a stack by just giving a number. So there, the Campana theory becomes like a totally different beast compared to a stack theory, because Campana does not specify what the inertia groups are, whereas in stack theory you do. And you already see this in complex geometry once you're talking about singular spaces, because the local fundamental group of a singularity can be very interesting. And you might not even be able to speak of a root stack when you're given a divisor and a number, but the Campana thing still gives you something meaningful.
I see. Thank you very much.
Sure.
Yeah, so thanks for the first half, and I think you can just continue, with the second half as if it was a single talk. Oh, I see slides for the second half. Okay.
Yeah. You will recognize that they're kind of similar to what you've seen in Italy, or maybe nearly identical, except that I changed the title and a few other things. So a second half of the talk, I'll be talking a bit about the basics of Campana's theory of C-pairs again. I should grab my notes so I know what's coming. And then tell you where all this is headed and what we're interested in. So basically, to give the message away immediately, what we're interested in is, as a near-term goal, to construct an analog of the Albanese variety for Campana C-pairs. And why are we interested in? We are interested in this because there's a host of problems, mostly concerning rational points, entire curves, hyperbolicity properties of varieties, where basically all the results that we know are for subvarieties of abelian varieties. If you have a variety, you ask yourself how many rational points does it have and how they're distributed. If you are in a subvariety of an abelian variety, then you can say things, and otherwise, typically you cannot. And our goal is to break a little out of this restraint by replacing our abelian varieties by a more general class of abelian varieties of C-pairs, and thereby emulate results that are known classically for abelian varieties in the C-pair context, and maybe get a few more general results. So this has two strands to it. There's the complex analytic side, where you talk about entire holomorphic curves. And there's the other side of the Voita mirror, which is rational points and maybe more interesting fields than the complex numbers. But about this, I won't be saying anything today. Right, so outline of this talk. Be a little more specific about C-pairs of their differentials, then define C-pair analogs of classical invariants that we know from complex analysis, irregularities. How many one forms are there? Talk a bit about the category of morphisms, which I already mentioned when I compared my spaces to root stacks. And eventually say a few words about our construction of the Albanese, or our hunch what an Albanese for C-pairs could possibly be, and start out with a few results in the direction that I already mentioned, entire curves and hyperbolicity. Right, so C-pairs and their differentials. I already introduced a few words here. A C-pair is a pair of a normal analytic variety that is welcome to have rather nasty singularities. So definitely we don't want to restrict ourselves to a Kawamata log terminal or log canonical or anything. There's reasons to allow arbitrary singularities here. Yeah, we have a device here that has standard coefficients. I already introduced them. In the full-blown theory, these conditions are natural numbers or maybe infinity, where infinity gives you the logarithmic case. But for simplicity today, let's say we don't want infinity. We look at the case only where the mi integers, and we have no logarithmic parts in our boundary. Everything I'm going to present today will be valid in the logarithmic setting, but it turns out that we are working in the analytic category here. And when you say Albanese in the analytic category, as soon as you have a logarithmic component in your boundary, then the definition of the Albanese is really complex. This is there are some new features that you haven't seen in we haven't seen in algebraic geometry, and I would like to avoid discussing that. So right, And as I already mentioned, if I have a compact Kähler space, we have C pairs that interpolate between the two cases, the classic geometry of the compact space X. And if the MI are all infinity, which is something I'm not having today, then we get the geometry of the logarithmic pairs. And as I already pointed out, what we would ideally like to come up with is a sheaf of differentials forms that have log poles of order given by the divisor coefficient along that divisor. And right, we know that isn't possible, but what we have is that on suitable covers, it's possible to define a sheaf that looks like the pullback of our hypothetical sheaf that doesn't exist because the root functions is not well defined. Right, let me draw this silly little picture here. So we have X hat, we have X, we have gamma, which is Z goes to Z square. This sheaf should be something like 1 over square root of X dx in this simplest setting. And that doesn't exist. But then, of course, when I take the pullback, the gamma pullback of this hypothetical differential and apply the formal rules of differentiation to it, then out comes 1/2 times dx. So for this simple case where I have A1 covering A1, a sheaf that looks like the pullback of our hypothetical sheaf would simply be the sheaf of all differentials on X hat. Now, if I raise the intersection, the branch multiplicity by looking at the morphism of the form Z goes to Z to the M, then the hypothetical pullback that I obtained by applying the formal rules of derivation will be a sheaf of differential forms that has zeros to a certain order. And this is precisely what I mean by sheaf of adapted differentials. This is differentials that have zeros of the form that I would get if I take my hypothetical sheaf downstairs, pull it back, and apply the formal rules of differentiation to figure out what it is. Right, this can be made more precise on singular spaces. On singular spaces, we have learned in the course of the years that if you want to study differential forms, then Kähler differentials might not be your best friend. Much of the geometry is encoded not in Kähler differentials, but in the reflexive hull of Kähler differentials. So this is the sheaf here. So omega p is the sheaf of Kähler differentials, omega px, and then double dual. An analogous construction gives you a reflexive hull of the sheaves of differentials, and these are uniquely characterized by universal properties. If you want to formulate the universal properties precisely, then your best bet is to ask Pedro. who has written a PhD thesis about this. Right. There are a few simple cases. Simple case is d equals 0. We have no boundary. Then our hypothetical sheaf is the sheaf of reflexive differentials without any poles. So it's just a sheaf of reflexive differentials. And the sheaf of adapted differentials is simply the sheaf of pullback of adapted pullback of reflexive scalar differentials. Right. And if your divisor becomes larger, then the sheaf of adapted differentials also becomes larger. So bottom line is when I have a C pair, I have a notion of differential forms. I have a notion of differential forms. These differential forms, they do not exist on our original space. They exist on suitable covers where the ill-defined or multi-valued root functions become well-defined. And then by using standard tricks of category theory or some elementary construction, there's a way to define sheaves on arbitrary covers or quasi-finite morphisms. And this is the sheaf of adapted differentials, and this is the main player that we're looking at today. Right. Then there's irregularities, and yeah, the irregularity is typically in classical geometry. If you have a space, then you look at the irregularity, which is the dimension of the space of one forms. Now here, our situation is a little more interesting because everything depends on a cover. So the one forms that we're interested in exist on the cover. They exist on the cover. So in order to say irregularity, we have to specify what cover we would like. And but then once you choose a cover, then you have these adapted differentials, you have adapted one forms, and you can ask for their dimensions. So this is simply a subset of H naught x hat omega 1 x hat. So this is not a subset, it's a smaller number, or maybe equal. Right. So we have an adapted irregularity that depends on the cover. We don't know how it behaves when we move from one cover to another, but we could take the supremum of all covers and call this the augmented irregularity. In analogy to the augmented irregularity of Kähler manifolds that has been discussed a lot by Deki Zhang from Singapore. Right. So we have an augmented irregularities, and we would like to understand what they are. So here is
sorry, can I ask about the inequality? So
yeah.
So the inclusion we had in the last page is so reflexive differential is inside the adapted differential. Yeah.
Yep. So I forgot the log. You're right. Sorry for that.
Log.
Like so. Yep.
Thank you.
Thank you. Right. So yeah. So we have these irregularities. These irregularities are, I think, very interesting invariance. Also the augmented irregularity. And what we don't understand, and what I would really like to understand much better than I currently do, is how do these irregularities depend on the choice of the cover. So that was the next slide. So could it be, so already in the simplest case where d equals 0, so if d equals 0, say everything is smooth, you have a space that maybe has no differential forms. You go to a cover and you look at adapted differential forms. So adapted differential forms, if d is 0, is a very simple thing. It's simply pullback of omega 1x. Now, how does that behave when you have various covers? So could it be, for instance, that it sees the Galois group? Could it be that the pullback of omega 1 never has a section unless your Galois group is very complicated? Could it be that it's 0 as long as the Galois group is solvable, and then maybe becomes supersize once your Galois group factors via the Fischer-Grace monster group or Mathieu Moonshine or you name it? Something that has to do with what are they called? Automorphic forms. I don't understand this. And a similar question when you're dealing with singular spaces. Could it be that the pullback of omega 1 never has a section as long as your space is smooth or has like mild, the covering space is smooth or has mild singularities, and sections only appear when you have sections that are, say, worse than log canonical or worse than rational? The answer is, again, I don't know. I don't know, but I would really like to understand this better. A similar question for people who are already fluent in Campana theory. Campana has this word special, which I haven't even mentioned so far. If you know what it means, then you might want to ask, how is this augmented irregularity related to the word special? I would expect that special implies that the augmented irregularity is finite, but then again, I don't know how to prove that. Right. So then, I would like to move in the direction of the Albanese. So let's say I have a C pair, X, D, and I have a cover. Then upstairs, I have the Albanese of the cover. And the Albanese of the cover, maybe I ignore for a second that the cover could be like very singular. Let's look at the simplest case first. The Albanese of the cover is the universal space where all the one forms come from. It's the universal space where all the one forms come from. And some of these one forms will be adapted and others maybe not. When I would like to discuss the Albanese, I would like to discuss an Albanese that has to do with adapted differentials only. So what I consider in this context is the largest quotient of the Albanese. This is this B gamma here. The largest quotient of the Albanese such that all differential forms coming from this quotient are adapted. This largest quotient always exists. It could be a point. It could happen that on X hat I have many adapted differentials, but not a single one of them comes from a torus. So in that case, B gamma would be a point. It could happen that B gamma is an interesting torus where all the adapted differential comes from, or it could be that I'm in an intermediate situation where I have two classes of adapted differentials, some that come from a torus others that do not come from a torus. I find this very interesting. But no matter what, a B gamma simply exists as the maximal Lie group quotient that exists by general principles. Yeah, and then again, I can ask, or I can define the space of adapted differentials that comes from a universal torus quotient B gamma, and I call the size of that space the Albanese irregularity of the cover, and then I can then again take take the supremum of this over all covers and look at the augmented Albanese irregularity. I believe these are very interesting invariants, and these might be interesting, I think, also already in a setting where D is 0. I don't understand. Right.
And also,
D
could I
is
ask?
0.
Sorry. So why do you use the term Lie group instead of just so torus?
Because I'm in the Kähler setting. Oh,
Torus.
oh yeah. You want torus?
Torus.
I have no
totally
problem.
Fine. Okay.
I have no problem saying torus. The only thing I want is a compact torus. I don't want something like in the Albanese modding out a subgroup that's dense and then end up with a non-Hausdorff space for B gamma. So I want the quotient to be an honest torus and not a topological group that is not Hausdorff or something.
Okay.
Does that answer the question?
Yeah, thank you.
Right. So yeah. So this is interesting already in the simplest case where D equals 0, and then I have my omega 1 x d gamma. Here's gamma is simply gamma pullback of omega 1 x. If everything is smooth, already there, I might be in a situation. So this is now a subset of omega 1 x hat. I might be in a situation where some of the sections here come from a torus quotient, others do not come from a torus quotient, and I can't say I understand the geometric significance, but these things are so naturally there that I'm very much convinced they must be geometrically meaningful. Right. So maybe I should point out we have these invariant by construction. There's inequalities between them. This is the dimension of the space of all adapted differentials. Some of them might come from the torus quotient, others not. So there's an inequality here. Same then with the augmented inequalities. We have examples coming out of prim varieties where the inequality in the first line can indeed be strict, already for curves. So you can find curves, no boundary. You find a cover of the curve where you have adapted differentials, but not a single of the adapted differential comes from a torus quotient. But it could be that maybe we are looking at the wrong cover. So if we go to higher covers, then maybe the difference goes away. We don't know. So we have an example where the inequality in the first line is strict, but we don't know what happens when we go to the supremum over all covers. There we might have a different picture. And we don't understand the difference yet. But Hervé Rousseau is visiting not only Taipei, he'll be in Freiburg in February. And then hopefully we can look at this and maybe we'll be able to work something out. Who knows? Next is morphism of C pairs. And the notion of morphisms that we would like to propose is, in a sense, the most simple and the most natural you can look at. So we have two C pairs. We have a morphism between the underlying complex spaces, and we ask ourselves, when would we like to call such a morphism phi a morphism of C pairs? And a morphism of C pairs we would like to propose is morphisms where adapted differentials pull back to adapted differentials. So we're under the impression that the notion of adapted differentials is what makes Campana's theory fly. And so a morphism should be called morphism of C pairs if and only if it respects the most basic objects of the theory, that is adapted differentials. Catch is adapted differentials don't live on X or Y, they live on covers. And we have many covers. So to be more precise, the definition that we would like to propose is we call phi a morphism of C pairs if for any commutative diagram where we have a cover of X, we have a cover of Y, and then a morphism between the cover that makes the diagram commute, then the differential upstairs pulls adapted differentials back to adapted differentials. Right. So what does that mean? We worked out some examples. One example is the thing that I already mentioned in the pre-talk. When you have a space, you have a divisor that appears with multiplicity m minus 1 over m, and you have, say, C here, you have a curve. You ask yourself, is this curve or this entire curve C a morphism between C pairs? And if you work out the definition, then it's a morphism between C pairs if the image, if it intersects my divisor D at all, it must intersect with multiplicity m or higher. And that, as I pointed out, is distinctly different from the situation that you have when you're discussing root stacks. So this is already an interesting example that has a bit of a history in arithmetic geometry, but I would rather not go into this today. Instead, I think maybe even more interestingly, there's a non-example. The non-example is the following. So I have a quotient singularity of the simplest form that I can think of, a quotient singularity that looks like C, C2, and here is C2 modulo plus minus 1. So the simplest quotient singularity that we can look at is the A1 singularity. And I can blow up the A1 singularity and get a space here that is smooth, has an exceptional divisor E, and E is isomorphic to P1. And we know the normal bundle of E inside, so this is Y, this is X, inside X is OP1 of minus 2. And now I ask myself, do I get a morphism between X, or do I get a morphism of C pairs between X0 and Y0? And the answer is no, this is not a morphism of C pairs. This is not a morphism of C pairs. And how can I see that this is not a morphism of C pairs? I need to check that It's a morphism of C pairs if for every commutative diagram upstairs, adapted differentials pull back to adapted differentials. So in order to see that this is not a morphism of C pairs, it suffices to construct a single diagram. And here's a diagram. So I have my A1 singularity. I present it as a quotient locally as a quotient of C2. And I can take the fiber product. The fiber product is simply the blow up of this smooth point. So this is y hat, this is x hat, and this is blow up of y hat in a smooth point. And of course, here on y hat, I have the action of the group Z2, which maps every vector to minus that vector. And that action also exists on x hat. It's an action that leaves every point of the exceptional curve fixed and flips all the other points. And the morphism here that I get from the fiber product is simply the quotient by this group. So the vertical arrows in this diagram, these are group quotients. Now, what about adapted differentials here? So here, an adapted differential on x hat is simply a pullback of a differential on x. That's a condition. Not every differential form on x hat is locally a pullback. Here, it's very interesting because the branch and ramification locus, they are points, and reflexive hulls don't see points. So if you work out the definition of adapted differentials, you find that on y hat, any differential is adapted. Because away from the singular point, your morphism is étale. So if I ask myself, is this a morphism of C pairs? If I ask myself, is this a morphism of C pairs? I'm asking, is it true that any adapted differential on y hat, that is any differential, pulls back to a differential on x hat that's adapted over x? And this is a serious condition. And the answer is no. The answer is no. So this morphism from x to y is a morphism of a manifold into a singular space. And even if I take zero boundary, this is not a morphism of C pairs. So you asked for a difference between C pairs and root stack picture. Again, there's a difference here. If you have a zero boundary, the root stack will be trivial, and any morphism will be a morphism of stacks. But here we're having non-trivial local fundamental groups, and you see the morphism, the notion of Campana C pair sees that. The notion of Campana morphism sees the local fundamental group. So right. Let me erase this again and come back to the original slides. We have the morphism from a Kummer K3 to a torus quotient. Locally, it looks like blow up of A1 singularities in a point. And this isn't even a C morphism locally. This is not even a C morphism locally. And I claim this is philosophically correct. This should not be seen as a C morphism. Because the geometry of the K3 surface and the torus quotient is hugely different. I mean, these are spaces where these are even projective spaces or projective varieties where the canonical class is trivial. So they carry a natural Kähler-Einstein matrix On the smooth L space, this is your solution to the Calabi conjecture. On the singular space, this is the generalization of the Calabi conjecture to spaces with canonical singularities. The two Kähler-Einstein metrics that we get on the Kummer surface and on the torus quotient are, however, fundamentally different. The torus is flat, the torus quotient is flat, but the Kummer K3 is not flat. It has non-trivial holonomy. And that's why I think philosophically the morphism shouldn't be considered a morphism of C pairs, because the geometry between them is way too different. So I believe that fundamentally this is correct. If you want this to be a morphism, you have to add the exceptional divisor with multiplicity 1/2, where 1/2 is of course the order of the local fundamental. Right. So bottom line and summary of all this, we have a notion of morphism of C pairs. It's a natural and functorial, and Pedro can point out what it means. It ties in with notions of the minimal model program. We have categorical quotients the same way that you have categorical quotients in the category of algebraic varieties or complex analytic spaces. And very interestingly, if you have a torus quotient and you have a morphism between them, torus quotients could be rational varieties. They could be basically be of any geometry. And there are lots of morphisms between them because the automorphism group of these rational varieties tends to be large. But very few of them are C morphisms. When you have a C morphism between a torus quotient, then it respects the group structure. So it comes from a Lie group quotient. This is a non-trivial statement and it needs to be proven. So, right, now let's move to the last part of this talk, the Albanese. I already said why we're interested in the Albanese. We're interested in the Albanese because we would like to generalize results in the direction of length conjecture, hyperbolicity, rational points, entire curves, where the best known results are only known for subvarieties of abelian varieties. Right. The Albanese has many definitions that in the complex analytics setting are all equivalent. I will come back to this later. But we are trying to follow the definition that was proposed by Sayre, who said that the Albanese of a projective variety is the universal morphism to an abelian variety. We believe that the C-pair analog of an abelian variety should be a quotient of an abelian variety, or in the complex setting, should be a quotient of a torus. And we emulate Sayre's definition that we say the Albanese of a C-pair should be the universal map to a torus quotient. We prove that an Albanese exists if the Albanese, the augmented Albanese irregularity is finite. And if it's infinite, then we still get an Albanese variety, but with a universal property that's a little weaker than that proposed by Sayre. It might still be useful, but we haven't really formed an opinion yet. However, I should point out that there is interesting classes of varieties where the Albanese irregularity is known to be finite. In particular, that holds for every variety that's special in the sense of Campana. Right. And then as a first application or indication that this notion could actually be useful, we propose a general result that was already known by work of Kawamata for entire curves. So you have a space, complex scalar manifold, maybe projective manifold, and you look at entire curves into that space. So holomorphic maps from C into this space. And you ask yourself, is it possible that the image of that entire curve will be dense? Can it be dense? And a classic result known as the Bloch-Occhiai theorem, what was really proven by Kawamata, is that if you have a space whose Albanese is large, then entire curves can never be dense. And we propose a C analog of this. If you have a C pair whose C Albanese is large, then C entire curves, so holomorphic C morphisms from the complex line into your pair x comma d can never be dense. That is to say, they're algebraically degenerate. The risky closure is not everything. Right. The proof is involved. It applies a bit of Nevalina theory. And basically, the proof is reformulating results of Noguchi as a form of Nevalina theory for C pairs. But that would be a different talk. So I guess I'm a little early, but maybe I should end the talk here. Maybe as a last thing, I should point out or summarize, we have a very natural notion for an Albanese of a C pair. We can emulate some classic results about the Albanese. There's, of course, so much more that you want to know. But we know only in part what our Albanese means. The classic Albanese, you know, it has three different meanings. It's the universal space. So following Sayre, it's the universal morphism to a torus. So this is also our definition. It's the universal space where all the differential comes from. And it's the Shafarevich map for the abelianized fundamental group. We would like to say that our Albanese can also be characterized as the Shafarevich map of something, or as the universal space where all the differential forms come from. But we don't know how to do that yet. This is an open question for research. And with that, I would like to conclude 10 minutes early. Thank you for your time.
Yeah, thank you very much. And maybe now let's ask if there are any questions in the audience.
So could you please say a bit more about what does weaker variant mean for the Albanese? And why do you only expect that some weaker version exists? So is it known that the stronger versions doesn't exist? For
yes.
some...
So fact is, maybe I can. Fact is an Albanese exists if and only if Q plus alp is finite. So a weaker version of the Albanese. What does that mean? So the Albanese typically is so in the classic setting. We get an abelian variety. Get an abelian variety A and a morphism, say, alb from our space X into our abelian variety, and that be the image, right? So we get a morphism from X to an abelian variety. That morphism is typically not surjective, so it has an interesting image variety Z, which is maybe not normal, but this is something that we would typically discuss. So Z or its normalization is where we know all properties concerning rational points, hyperbolicity, blah, 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 blah. Right. So the weaker version, so this is the classic, and the weak version is we get Z, but this Z comes with no preferred embedding into an abelian. It has an embedding into an abelian variety, but it might have many embeddings into an abelian variety, and that embedding is not canonically given. That embedding is not canonically given, and when I say this might be just as useful, because then, so we have a universal object Z. This Z is embeddable into an abelian variety, so we know that this Z has all the properties that we want, rational points, hyperbolicity, because it's embeddable. But it does not come with a unique embedding. So that makes the universal property worse, but maybe not less useful.
So even the abelian variety is not unique, or just embedding not unique.
Yeah. So there's a sequence of abelian varieties of larger and larger dimensions, or torus quotients. We're talking C pairs here. And that can be embedded into any one of those of increasing dimension. But there's not a preferred one.
Mhm.
So this is something that you don't see for in the classic picture. But again, maybe you don't care about having a precise embedding. In settings where you just need that you have one embedding, that's good enough.
Hmm. And also for log variety, there is a log version of Albanese variety which would be semi. I think, yeah, would be a semi-abelian variety. So, is it the reason that you only discuss about so coefficient? Yeah, m not, yeah, finite coefficient in your talk.
Yes and no. So what I should say is that the whole theory works in the in general, no matter what the coefficient is. The problem that I wanted to avoid is the following. So maybe I should add a new page. Here's a new page. So when you have classically you have a logarithmic pair, right? Then you get a quasi-Albanese is a morphism from X minus D into a semi-torus, correct?
Mhm.
Are you happy with this or not?
Yes.
Okay, this semi-torus, so your x minus d is embedded into x. And so this is the Albanese of x minus d. You have the Albanese of x, and this is a torus. And when you have a morphism between spaces, then you get a morphism between Albaneses. So this is a C star to the n bundle. So you get an exact sequence like so. Right. This is called a presentation of the semi-torus. And when you have a presentation of a semi-torus, then you have this C star to the n bundle you can compactify to a Pn bundle. And your Albanese map here is not just any Albanese. So this has a compactification. You have a compactification like this. And your Albanese, which is a holomorphic map from x minus d to the semi-torus, gives you a meromorphic map between compactifications. So why am I telling you all this? Because the universal property in the analytic setting says that the Albanese map here, this is the universal morphism into a semi-torus. So this is what. So in the algebraic setting, the Albanese map is the universal map into the semi-torus. This is wrong in the analytic setting. In the analytic setting, the Albanese is universal for all maps into a semi-torus that extend to meromorphic maps of this compactification.
But then in the analytic setting, you also have different choice of compactification. So which
Absolutely, you have different choices of compactifications, and they might not be bimeromorphic.
So is there a privilege? When you say this universal property in the analytic setting, do you choose a privileged compactification or?
Yeah, you choose a privileged compactification that comes from the C star bundle structure. Because this can always be compactified to a Pn bundle structure.
Yeah.
So the Albanese in the analytic setting is not just a semi-torus, it's a semi-torus together with a bimeromorphic equivalence class of a compactification. And whenever so these are many syllables, and this adds a layer of complexity that you haven't seen in algebraic geometry. So, and I wanted to avoid discussing that.
I see. Thank you.
Sure. Yeah. So the notion, for me, this was a very tough lesson. The notion of a quasi-Albanese in the analytic world is much more complicated than in the algebraic setting, because in the algebraic setting, compactifications are birationally unique. In the analytic world, this is no longer true. So you have to carry these bimeromorphic equivalence class around as part of your data.
Thank you very much.
Sure.
So are there any more questions from the audience? So maybe I ask some quick questions. So for morphisms, generically finite morphisms to abelian varieties, there's this structure theorems for the push forward of the canonical, this
Mhm.
Chen-Yang decomposition. And I was wondering if maybe something like this could be generalized to this setting when you have this replacement of abelian variety by C pairs, Torus quotients.
I understand the question. I would expect yes, but nobody's done it.
Oh,
The whole theory is too new, so there are all these structure results for varieties that are of maximal Albanese dimension. They have all sorts of geometric and arithmetic properties, and I would expect that much of this carries over to our generalized setting, but none of this has been done yet.
I see. Okay, thanks.
Mhm.
Any more questions?
Maybe another quick question. So we also have so analog of Kawamata's surjectivity result for Kodaira dimension 0 variety.
Yeah. So what we have is we have a result like this for varieties that are Campana special. For varieties, does that? Okay. I have a blank right now. Pedro, Kodaira dimension 0 implies Campana special?
So a priori, yes, but I'm not
Okay,
100%
then
sure, but I would say yes. Yeah.
I believe yes. So then we have that result. You
for
can also
every-
ask about the structure of a fiber space, and there we haven't given it any thought yet.
Okay. So you are saying that for Campana spatial we have surjectivity.
Yeah.
Thank you.
Any other questions? No? Then yeah, let's thank the speaker again. Thank you very much.
Thank you very much.
It's been my pleasure.